This lecture highlights the growing significance of interdisciplinary collaboration in urban ecological design, a field that sits at the intersection of environmental science, spatial planning, and social innovation. Defining interdisciplinary approaches in this context requires not only understanding the theoretical foundations of ecology and urbanism but also recognizing the methodological frameworks that allow diverse fields, such as architecture, landscape design, sociology, engineering, and public policy, to work cohesively. Interdisciplinarity in urban ecological design emphasizes systems thinking, where cities are understood as dynamic socio-ecological systems shaped by both natural processes and human decisions. Identifying how multiple disciplines collaborate for eco-urban solutions further reveals the importance of integrated workflows and shared value systems among professionals. For example, ecological or environmental scientists may supply data on habitat needs and ecosystem services, while engineers translate this knowledge into infrastructure solutions, and planners embed those solutions into regulatory tools. Designers contribute by implementing measures into the landscape, and social scientists ensure that outcomes are equitable and community-centered. Effective collaboration depends on transparent communication, iterative design processes, and tools such as GIS, participatory planning methods, and multi-criteria assessments that help align disciplinary perspectives. Ecological spatial planning provides the analytical framework for understanding landscape processes and environmental constraints, thereby creating the foundation upon which effective eco-urban solutions can be designed. By integrating spatial ecological data with urban development strategies, planners can generate interventions that enhance both urban resilience and long-term ecosystem quality. An eco-urban solution can be understood as a set of measures, technologies, and planning approaches aimed at achieving several interconnected goals. Reducing the environmental impacts of urbanization. This includes strategies that lower pollution, minimize resource consumption, and reduce greenhouse gas emissions. Typical measures involve cleaner mobility systems, energy-efficient buildings, circular economy approaches to materials, and nature-based methods for managing stormwater or improving air quality. The objective is to ensure that urban growth does not degrade ecosystems or exceed environmental limits. Enhancing ecological functionality. Eco-urban solutions strengthen or restore natural processes within the city. This may include improving soil permeability, increasing proportion of vegetation cover, supporting biodiversity through habitat creation, or reconnecting fragmented green corridors. By integrating ecological principles into planning, cities can regenerate ecosystem services such as cooling, water retention, carbon sequestration, and habitat provision. Increasing climate resilience. These solutions help cities adapt to climate risks, such as heat waves, floods, droughts, or strong winds, while also mitigating their impacts. Examples include green infrastructure for water retention, reflective or vegetated surfaces to reduce the urban heat island effect, and multifunctional landscapes that perform both ecological and protective roles. The aim is to ensure that urban systems remain functional under changing climatic conditions. Improving the quality of life for residents. Eco-urban solutions also contribute to social well-being. They create healthier public spaces, enhance thermal comfort, provide opportunities for recreation, and strengthen community engagement. Better air quality, quieter streets, accessible green areas, and more attractive public spaces directly support physical and mental health, making cities more livable and inclusive. These categories represent key areas of eco-urban solutions, each contributing to greener, healthier, and more climate-resilient cities. Blue-green infrastructure. This set of measures integrates water management and urban vegetation to enhance ecological performance. Green roofs and facades improve insulation and reduce heat stress, while rain gardens and bioswales naturally manage stormwater and support infiltration. Urban forests and street trees help regulate microclimate, capture pollutants, and increase biodiversity. Revitalized rivers and urban reservoirs restore natural hydrological functions and create attractive public spaces. Measures improving microclimate and environmental quality. These solutions address heat, air pollution, and overall comfort in dense urban areas. Vegetation, reflective materials, and shading systems reduce the urban heat island effect. Increasing biodiversity in streets and parks strengthens ecosystem stability and recreational value. Ecological soil and water management ensures healthier vegetation, better infiltration, and improved retention during heavy rainfall. Low carbon and energy-efficient systems. These measures support the transition to sustainable energy and resource use. Decentralized renewable energy sources, such as rooftop photovoltaics or heat pumps, reduce dependency on fossil fuels. Energy communities allow residents and institutions to share locally generated energy. Passive and adaptive architectural features, e.g., natural ventilation, shading, thermal mass, increase building efficiency and resilience during heat waves. Mobility and urban planning measures, these strategies shift urban transport toward sustainable modes and improve spatial connectivity. Cycling pathways and public transport-oriented development reduce car dependency and lower emissions. Traffic calming enhances safety and promotes active mobility. Green corridors and pedestrian links between neighborhoods and surrounding landscape improve ecological continuity and create pleasant, accessible routes for everyday movement. Digital and systemic solutions. Digital tools allow cities to plan and manage resources more effectively. GIS and digital twins simulate climate impacts and test adaptation strategies before implementation. Together, these measures illustrate how ecological, technical, and spatial solutions can be combined to create truly sustainable and resilient urban environments. Successfully implementing these measures requires the collaboration of many different professions, including experts in urban planning, engineering, architecture, ecology, environmental sciences, transportation, energy systems, and information technologies. Only through interdisciplinary cooperation can eco-urban solutions be effectively designed, executed, and maintained. Here you can see an overview of the key professions involved in designing and implementing green and resilient cities. Other professions that contribute to spatial planning, public interest protection, and regulatory decision-making will be presented on the next slide. This interdisciplinary structure shows how landscape architecture, and urban planning, civil and environmental engineering, sociology and public health, as well as information technology, GIS, come together to create cities that are not only functional and attractive, but also resilient, climate adaptable, and environmentally responsible. This overview is not exhaustive. It is important to emphasize that many other professions can also be involved in the process, such as demographers, transport planners, utility managers, and energy systems experts. Together, they expand the interdisciplinary collaboration necessary for the sustainable development of cities that are long-term sustainable, resilient to natural hazards, and pleasant to live in. Within each of the disciplines mentioned, there are also specialized subprofessions that play a key role. For example, within environmental engineering, it is appropriate to involve specialists such as hydrologists, climatologists, or experts in urban greenery, e.g., mature trees, park design, and green infrastructure in general, including green roofs, rain gardens, and other innovations that help mitigate the urban heat island effect and improve water retention. It is essential that these professions cooperate with each other. Without integrating common solutions, it is not possible to achieve responsible and sustainable development of the territory. Each field brings specific knowledge, technologies and analytical tools that help create an integrated design. 1. Landscape ecology analyzes the structure, functioning and dynamics of the landscape, examines in detail, for example, biological processes, mutual interactions between hydrology and the microclimate of the area, and based on this knowledge, measures supporting biodiversity, ecosystem services and landscape connectivity are proposed. Experts in this team determine the limits of the landscape, propose ecological zoning according to the carrying capacity of the territory and carry out monitoring and data collection in order to model the impacts of urbanization and propose appropriate natural or technological solutions to problems. 2. Data science and GIS can create e.g. climate simulations and analyses of ecosystem services according to the landscape ecology data. The goal is to provide accurate geodata, e.g. for knowledge-based planning of changes in the landscape, monitoring the effects of proposed measures, and for making responsible decisions about the territory. 3. Landscape architecture and urbanism define the spatial arrangement, functional use of the landscape or city and create a hierarchy of public spaces. It is a tool for integrating the proposed solutions to problems into planning processes and regulatory instruments, such as the spatial plan. 4. Civil, water management and environmental engineering designs the technical components of systems, such as water management elements, retention systems, energy systems, transport infrastructure and of course the buildings themselves. It is a tool for implementing the intentions of not only ecological solutions proposed in spatial plans or supplementing common construction projects with ecological elements, e.g. rainwater management systems, green roofs. This procedure will connect natural systems with urban networks, sewerage, water, energy, transport. 5. Architecture works with the form, aesthetics, typology and function of buildings, integrates passive and adaptive principles into the built environment, and further connects public spaces with ecological functions and social activities. Very narrow, it cooperates with above-mentioned engineering disciplines. 6. Sociology examines the impacts on society, population behavior, demand for services, visions of future development and target environmental quality. The goal is to ensure that solutions meet real needs, are socially just and sustainable in the long term. When we talk about designing eco-urban solutions, it's important to emphasize that this process is not limited to planning, design, and construction professionals. Decision-making bodies play also a crucial role. Municipal and regional governments influence strategic priorities and allocate resources, while state authorities safeguard public interests, such as protecting agricultural land from excessive development and ensuring nature conservation. These governance structures work alongside technical and ecological experts to create integrated, sustainable solutions that balance environmental, social, and economic needs. In this context, we can highlight several key disciplines. Public administration. This field forms the backbone of public interest management. It focuses on policy development, administrative processes, and the implementation of measures. Public administration ensures that green urban projects align with strategic objectives, legal requirements, and public expectations. It also coordinates actions across different levels of government and stakeholders. Closely related is the understanding of decision-making mechanisms, which is essential for predicting political support for green urban initiatives and for designing participatory decision-making processes. Regional and urban planning. As a strategic planning discipline at municipal and regional levels, it ensures spatial coherence and long-term development. It integrates ecological principles into spatial and landscape planning as well as infrastructure development. Regional and urban planning provides tools for balancing urban growth with environmental protection and for embedding sustainability into regulatory instruments such as spatial plans. Economics and green finance. Economic analysis underpins resource allocation and cost-benefit assessments of proposed measures. Green finance establishes mechanisms for funding sustainable projects, which can include grants, climate bonds, and public-private partnerships. This discipline ensures that eco-city solutions are not only environmentally sound but also economically viable and attractive to investors and communities. Law, administrative and environmental law, legal frameworks define the boundaries within which urban development occurs. Administrative law governs procedural compliance, while environmental law protects public interests such as soil preservation, biodiversity conservation, and sustainable land use. These regulations ensure that eco-city projects adhere to environmental standards and contribute to long-term resilience. Interdisciplinary approaches help ensure that design solutions account not only for environmental performance, but also for social well-being, economic feasibility, and long-term adaptability. These approaches acknowledge that cities are complex systems in which natural, built, and social components interact dynamically. Key interdisciplinary approaches: systems thinking and socio-ecological integration. This approach views cities as interconnected systems where water, energy, biodiversity, transportation, and human activities influence one another. Evidence-based ecological planning. Ecologists, landscape architects, and environmental engineers collaborate to analyze ecological data, such as habitat networks, hydrological cycles, and microclimate behavior, to guide land use planning and urban form. This ensures that ecological functions, e.g., stormwater retention, carbon sequestration, pollinator corridors, are maximized through spatial design. Climate-responsive and resilience-oriented design. Urban climatologists, architects, and civil engineers develop strategies that mitigate heat islands, manage extreme weather, and enhance resilience. Participatory and socially inclusive design methods. Sociologists, urban designers, and community planners incorporate stakeholder engagement to ensure that ecological interventions also improve quality of life, equity, and cultural relevance. This includes co-design workshops, community mapping, and social impact assessments. Technological and digital integration. GIS specialists, data scientists, and urban planners leverage tools such as remote sensing, environmental sensors, digital twins, and parametric modeling to optimize ecological performance and visualize system-level impacts. Policy, governance, and economic integration. Urban economists, policy experts, and municipal planners align ecological design with regulatory frameworks, financing models, and governance structures. This ensures long-term implementation, maintenance, and cross-sector coordination. A good example of effective cross-disciplinary collaboration is the planning of green infrastructure, which requires the combined expertise of spatial planners, architects and civil engineers, climatologists, vegetation and urban greening specialists familiar with species suited to changing environmental conditions, hydrologists, and other related professions. To be effective, GI must combine both structural and functional dimensions of connectivity. GIS tools can support evidence-based design, but results require validation through field data and ecological assessments. Finally, GI must be institutionalized in planning policies, shifting from ad hoc projects to long-term systemic strategies for urban resilience. This slide presents 4 influential concepts in sustainable urban development. The sponge city model, pioneered in China, focuses on managing stormwater through natural and engineered systems. It promotes permeable surfaces, green roofs, and wetlands to absorb and reuse rainwater, reducing flood risk and improving water quality. The Smart Eco-City framework integrates digital technologies with ecological principles. It uses smart sensors, data analytics, and renewable energy systems to optimize resource use, reduce emissions, and enhance urban livability. Resilient city indicators provide a structured way to measure a city's capacity to withstand and recover from shocks such as climate events or economic disruptions. These indicators cover infrastructure robustness, social equity, and environmental health, guiding cities toward adaptive strategies. Finally, biophilic urbanism emphasizes reconnecting people with nature in urban environments. It incorporates green spaces, biodiversity corridors, and natural elements into city design, improving well-being, reducing heat island effects, and supporting ecological resilience. Together, these frameworks illustrate how cities can combine technology, ecology, and design to create sustainable, adaptive, and human-centered urban systems. The sponge city model, developed in China, represents an innovative approach to managing urban water challenges. Its core principle is that cities should function like sponges, absorbing, storing, and purifying rainwater, then releasing it when needed. This concept addresses 2 critical issues: urban flooding and water scarcity. Key features include permeable pavements, green roofs, rain gardens, and wetlands or retention ponds. These elements work together to reduce surface runoff, improve water quality, and enhance groundwater recharge. The ultimate goal of the sponge city model is to strengthen urban resilience to climate change by integrating natural processes into urban infrastructure. It demonstrates how ecological design can complement engineering solutions to create cities that are adaptive, sustainable, and better prepared for extreme weather events. The Smart Eco-City framework combines advanced digital technologies with ecological principles to create sustainable urban environments. Its core idea is to leverage data-driven systems to optimize resource use and improve quality of life. Key components include ICT and IoT solutions, such as smart sensors for monitoring energy consumption, water management, and traffic flow. These technologies enable real-time data collection and informed decision-making. The framework also emphasizes renewable energy sources, solar, wind, and energy-efficient systems, to reduce carbon emissions and support climate goals. In addition, green infrastructure elements like parks, green roofs, and biodiversity corridors are integrated to enhance ecological connectivity and urban resilience. The ultimate goal is to create cities that are intelligent, environmentally responsible, and socially inclusive, where technology and nature work together to deliver sustainable growth and improved living conditions. This slide presents the core indicators used to assess urban resilience, the ability of a city to withstand, adapt to and recover from shocks and stresses such as natural disasters or the impacts of climate change. Examples of these indicators serve as benchmarks for assessing both the physical and social dimensions of resilience. Infrastructure resilience ensures that critical systems, transport, energy, water, can continue to function during crises and are designed for rapid recovery. Emergency preparedness measures the effectiveness of disaster response plans, early warning systems and community preparedness to minimize losses and disruptions. Social equity and inclusion emphasizes the importance of equitable access to resources and services, reducing the vulnerability of marginalized groups and promoting social cohesion. Ecosystem health recognizes the role of natural systems in mitigating risks, e.g., flood protection, air quality, and maintaining long-term livability in cities. Biophilic urbanism is an approach that integrates nature into urban environments to enhance both human well-being and ecological health. The concept is grounded in the idea that cities should reconnect people with natural systems, creating spaces that are not only functional but also restorative. Its core principles include the incorporation of green spaces and biodiversity throughout the urban fabric, maximizing natural light and ventilation in buildings, and introducing water features and ecological corridors to support habitat connectivity. The benefits of biophilic design are significant. It improves mental health and overall quality of life, mitigates the urban heat island effect, and strengthens urban ecosystems. By embedding nature into city planning and architecture, biophilic urbanism promotes resilience, sustainability, and a deeper human-nature connection in the built environment. Interdisciplinary approaches in urban ecological design refer to collaborative methods that bring together ecological science, engineering, architecture, urban planning, and the social sciences to create sustainable, resilient, and livable cities. These approaches recognize that ecological performance cannot be separated from social behavior, infrastructure design, or policy frameworks. By integrating ecological data, climate modeling, community engagement, and advanced technological tools, urban ecological design supports solutions that improve environmental health, enhance climate adaptation, and strengthen human well-being within urban environments. Ultimately, the successful implementation of these approaches requires close cooperation among diverse professional fields, including ecologists, planners, designers, engineers, architects, policymakers, and community stakeholders. Models such as sponge cities and biophilic design exemplify a holistic ecosystem thinking approach, demonstrating how urban environments can function as integrated socio-ecological systems rather than solely engineered constructs. By combining social, ecological, and technological knowledge, these frameworks enable innovative solutions that enhance urban resilience, support biodiversity, and improve human well-being. This integrative perspective not only broadens the design toolkit but also fosters adaptive strategies capable of responding to complex environmental and societal challenges.